3rd April, and today we are mainly going to talk about the model T5. Huh? GPT-2 is done. Matlab GPT-2 conceptually is done. Otherwise, it's a big paper. You can go and read the whole thing. But conceptually, what GPT-2 entailed is over. So GPT-2 mainly talks about two things. What are they? So one, it tells you that if you scale the model, it gives you something. You don't really need fine tuning. Okay. Another thing, that instead of modeling, conditioned on the input, you give output, and your architecture is task specific. What you do is, you bring task in the input itself. So probability, what you compute is given input and task, you compute the output. So that was one of the main key takeaways. Now we are going in the order in which these seminal papers were published. So today we are going to talk about T5, and so let me just give you a glimpse of the paper. So this is T5, exploring the limits of transfer learning with a unified text to text transformer. Okay. So T5 basically stands for text to text transformer. Okay. So T5, there are 5 T's: text to text transformer. Okay. Where transfer stands for this transfer learning. Now the paper is from Google, was published in sometimes around June, July 2020. That means after GPT-2. So we'll talk about what improvement it gives over GPT-2, but this paper is mostly a survey paper, in the sense that a lot of papers were being published at that time, which says use decoder only, make this size, train on this task, and this does well for all the downstream tasks. So too many people were changing too many things. This paper basically, so if you see their abstract, so let us go through the abstract properly. So transfer learning, where a model is first pre-trained on a rich data task before being fine-tuned on downstream task, has emerged as a powerful technique in NLP. Right? What is this first line? So you pre-train the model on a certain task. For us, what it has been, what was it for GPT-1? What was the task for pre-training for GPT-1? Language modeling. What was it for GPT-2? Language modeling. Right? What was it for BERT? Masked language modeling. Right? All right. So these are the things they are talking about, and then so you pre-train it on these tasks, and then you fine-tune it on the downstream task. GPT-1 and BERT, they both had this approach. What about GPT-2? GPT-2 says no to fine-tuning. It says, can we do something without fine-tuning as well? So can I make a generalized model which I don't have to fine-tune, and I am still able to do well on downstream tasks, be it summarization, be it translation, question answering, whatever. Okay. Now the effectiveness of transfer learning has given rise to diversity of approaches, methodology, and practice. Right. So too many people varying too many things. You have one idea, go and try to implement that. So in this paper, so this paper mainly talks about, so in this paper we explore the landscape of transfer learning techniques for NLP by introducing a unified framework that converts all text-based language problems into a text-to-text format. This is what we'll talk about in this lecture. Now, our systematic study compares pre-training objectives, architectures, unlabeled datasets, transfer approaches, and other factors on dozens of language understanding tasks. This is one of the key takeaways of this paper that we are not going to discuss much in detail. what they say is, and I will scroll through the paper, you will see that. See, what they primarily want to do is, so many people are trying to do so many things. So, some paper comes and talks about a particular objective for fine tuning. Some paper comes and talks about, says you have to increase the model size. Some paper comes and talks about, different objective, architecture, data sets, transfer approaches and so on. So, this paper says we are going to do one thing, we are going to compare across these ones, that is what is better. So, they do a lot of study on just comparing these pre-existing things. By combining the insight from our exploration with scale and our new, so again they give a new corpus. What was the corpus used in GPT-2? Note that GPT-2 is before this paper, right? That was 2019, this is 2020. Which? Web text, right? And that was crawled from links, outbound links of Reddit, having certain more than 3 likes or whatever. Now, this particular data set, I am not sure if I will get time to talk about it, but this is a subset of common crawl. Common crawl is basically dump of the whole internet. So, every month they do this dump. At that time it was around 20 terabytes, right? So, today it must be more, I think today it is somewhere around 42, 43 terabytes. But not everything will be high quality data there, that is why this text is usually not liked. So, they do a lot of pre-processing. From 20 TB they bring it down to somewhere around 750 GB. So, less than 5% of 20 TB. So, and then we achieve state of the art results on many benchmarks covering summarization, question answering, text classification and more. To facilitate the future our transfer learning for NLP, we released our data set, pre-trained models and code. Okay. So, that was this the general framework. Until then everybody used to release things on GitHub, the architecture, what else, data set and so on. Okay. So, this is what the paper talks about. Anybody has any questions here? What is this paper? What does this paper talk about? Let us just fix that part first. Its main what is that? Contribution, right? The main contribution of the paper is, according to them, is comparison between various parameters, but they also talk about one super important thing, that is looking back today we find that this thing is one of the rich findings that allowed ChatGPT to become ChatGPT, right? So, there are some 5 things that you can say made ChatGPT ChatGPT. What are they? First is transformer architecture. Okay. Second, the causal language modeling, which is you just get to look at the left hand side of the text. I mean, if your language goes from left to right, right? So, only on whatever you have seen until now you get to look just that. So, what is the other thing? Scale. So, GPTs, this is what we learned from GPT-2, that it says scale, I need big things. Last, I mean 3 done. Fourth is this T5, the objective, the framework that we will see here, and the last one is RLHF. RLHF stands for reinforcement learning with human feedback. Okay. So, finally we will talk about RLHF too, but this is the 4th thing that we are talking about right now. I think with this I will start. Let me pick up, what do I want to start. So, this is GPT-2 over. What is text to text format? So that's a good question. We'll talk about that. More? Transfer learning was a general term, so fine tuning came after. Transfer learning was mainly, at that time it was going on in computer vision, because it was very difficult to do transfer learning in NLP. But the moment transformers came, they made everything. See, in image everything is parallel. So if you are looking for, let's say, a ball in an image, and let's say this image is full thing. You have a ball here, here and here. Now it does not matter which part of the network you are looking for. Your same network should be able to tell me if there is a ball here. So it should be able to tell me there is a ball here, there is a ball here, there is a ball here, right? So that same network should be able to learn to recognize ball irrespective of where it is in my image. So on image, transfer learning was known pretty well, because the first initial layers will just do combination. So you will start with, remember that 28 cross 28 that we had done in machine learning? What was the name of the data set? MNIST, right? So it was a 28 cross 28 image. And what is the input that we give usually for DNNs? So we had this 28 cross 28, we flattened it. So we had 784 inputs, and each input correspond to the intensity of a pixel. So basically a number between 0 to 255. Okay. So you give input pixels, then next layers, they keep on combining them. So next layer will combine them and make lines. Next layer will combine them and make a bit more sophisticated structure, until you reach toward the end where you are able to construct the whole image in a certain sense. Okay. But coming back to transfer learning. Transfer learning is you learn for one task and are able to do other tasks from it. Whereas fine tuning is you've pre-trained on some task, and now you train it on this another task, the downstream task. But fine tuning means you don't need to train, for hundreds of thousands of examples. Just give maybe 5,000, 10,000 example, and that should be okay. So fine tuning is just, and fine tuning you can, so fine tuning means you have a pre-trained model and you are still training all the weights, but not that much, maybe by little bit. So fine tuning of those parameters specifically for that particular task. More questions? Okay. Alright, so what is the takeaway from T5? One, they compare a lot of architectures and present the results. Second, and that is more important for us, which is this T5. So I don't know how am I going to do it today, whether I draw. So, but let us do things on board. And then I'll come back to it if required. So T5 stands for text to text, what did we learn from, see, one of the things that GPT-2 paper wanted to do was, they said that you have this objective, this is the function that we are trying to learn, and then task is kind of captured in the model. This is the standard way of doing machine learning until now, right? And then GPT-2 paper comes and says, see, what you want is actually, and there was another paper by, McCann et al. So let me cite the paper. The paper is multitask learning as question answering. Okay. So this is the paper I am talking about. This paper and GPT-2. They talk about this. What I want is, instead of having everybody is okay with this, this is what I need to know. Anybody has any questions here? See, in every machine learning, what are we doing? We feed some input. So we compute probability of output given some input. That is what we are doing. And we have specialized architectures, models for a particular problem. So if you are doing translation, you have a particular architecture. If you are doing summation, you have a dedicated model that you are going to train just for summarization. So in case of summarization, your input will be the document, output will be the summarized text. But since all these are supervised tasks, so somebody should sit down and prepare this data set, and this is very expensive and time consuming. Okay. Now, what is it that we want ideally? So this is not GPT-2, this, let me write, this is what we have been doing until now. So maybe this is what traditionally done. Or this is what traditional ML. This is what traditional ML is, right? In GPT-2, they say that we are going to train on just one objective. What is that? Language modeling. Okay. And in GPT-2, the web text data set, they had said that, you know, that web text data set already has some, see, how would you start learning to do summarization just by being good at predicting the next token? How can you be very good at summarizing, question answering, doing NER, whatever? How can you be very good at these downstream tasks just by learning well to predict next token? No. What is language modeling? Language modeling is simply, I am given this corpus, I am given a context of 511, let's say, or 1023, and I am supposed to detect the, predict the next word. I learn just this objective, and I am able to do good summarization, I am able to do reasonable question answering, and so on. By giving the, so that is the whole catch here. You can't train on these separate data sets. See, what was the claim GPT-2 was making? Claim was, I train on only language modeling, and I am able to do the downstream tasks just by doing that. It would be cheating if I give it, you know, some examples of, so if I, let's say, take summarization corpus, I take question answering corpus, I take other these corpus, and also put inside my web text, right? Then I am essentially training on those things as well. I am kind of, it's not fine tuning, but I am using those corpus to train my model. So somewhere I am telling my model that these are the kind of tasks that exist too. They did not want to do this. You know, their title is very powerful. What was the title? Language modeling, language models are unsupervised multitask learners, right? So the title says language models are unsupervised multitask learners. So language models, just language models, are unsupervised means you are not supervised, you are not doing supervised supervised learning for which task? For summarization, for question answering, for this, for that, and so on. You are just doing one thing, that is called language modeling. And then you say, just by doing this, I am able to do summarization, question answering, and so on. Questions here? Okay. So what does no question mean? Is it okay? Okay. So this paper comes after GPT-2, and the trend that we have seen is Google has been doing mostly, Google has been kind of avoiding decoder only transformers until then. So they did publish a model called ExcelNet. If I remember it right, the name was ExcelNet, but from these papers we see that Google does not pursue this line of work too much. Okay, so, or at least researchers at Google. So this is traditional ML, and now they here come and say, so this is again from GPT-2, that this is what we want. Output, this is what we want. They don't necessarily do anything. So they say this would be ideal. So what should I write here? Input, comma, task. So what they are saying here is, I should remove my dependence on models. I train a separate model for summarization. I train another separate model for question answering, another for another thing. Can I get rid of this? They say instead of capturing task in model, I should be able to capture task in input itself. Okay. T5 to an extent answers this question. It does a hell lot of other things, but if you looking backwards, we see that what people retain from T5 is not those comparisons, but this task. So I am going to draw this task now. I won't do that, I will just go to the paper. So it's almost 70-page long paper. You can go and try to read it. Okay. Right. So this seems to capture the whole thing. T5 model. Full name was text to text transfer transformer. So green task is translate English to German, colon, this is good and das ist gut. Okay. So you feedback, you give model, what is it that you are giving? This is the input. How would you do it otherwise traditionally? You will say you are designing a translation model. So your model is to translate. You won't give this as input, you will give this is good as input and this should be your output. Right? Now, if you have another, so what is this cola? Something like linguistic acceptability. So corpus on linguistic acceptability, something like this. So you have a sentence and you are supposed to answer whether this is acceptable or not acceptable sentence in English. Okay. So this is a different data set, different benchmark. You are supposed to do this. Input is a English sentence and you are supposed to answer whether this English sentence is acceptable or not acceptable in a grammatical sense. Okay? So the course is jumping well. So the courses, they don't jump, so this is not acceptable. This is sentence, this is semantic text, what is the last word? Similarity. So semantic text similarity benchmark. Okay? You are given sentence 1, the rhino grazed on the grass. You are given sentence 2, a rhino is grazing in a field, and you are supposed to give the real number. Okay? Summarize. State authorities dispatched emergency crews today, Tuesday to survey the damage after an onslaught of severe weather in Mississippi. 6 people hospitalized after a storm in Atala County. How would you do these tasks otherwise? So there will be, so give me the architectures now. Translate. So you can use LSTMs or you can use the encoder-decoder transformer architecture that we had originally seen. Attention is all you need. This is what it does. It does translation. What is this? So you are either going to say it is acceptable or not acceptable. How would you solve this? It's a binary classification problem, right? So you are either going to say 0 or 1. What about this? You are supposed to give a score. So maybe take a dot product. Okay. So finally you get, what will you do here as an input? Tell me. Sentence 1 as input, sentence 2 as input, do something and finally give me a score. So sentence 1, sentence 2, and if you remember we had seen this in GPT-1 as well, there is nothing like, so compute similarity between sentence 1, sentence 2 and sentence 2, sentence 1 because their order should not matter in general. So you are supposed to give a linear number. Here again you have some dedicated architecture and this is what you are going to do. What does this figure tell us? T5 does it all for you. Okay, and how does it do? See the change here. It is not giving just examples. Every example is prepended with a task. Right? So you are basically kind of achieving what we had seen here. We wanted to input task, the input, whatever input was, and give output. Okay? And yes. Sorry? GPT-2 does not do that. GPT-2 says it would be awesome if we can do that. GPT-2 says that we give some inferences, right? GPT-2 does it the different way. I have not presented that here. For example, if they want to do summary, they will end a sentence with TLDR, right? Too lengthy, didn't read. So, and then it will try to summarize. But here they are explicitly doing it. So, how do you think this T5 is going to work? It's a transformer architecture. Which one? T5 is encoder-decoder, right? So it has both encoder and decoder. We'll see that architecture too. So you get the point here. How do you prepare your input in this case now? Right. So you take tasks based on all these, that data sets that you already know. Prepare prepare the aggregate of all these data sets as just one data set. You have to give prefix as the task that you want to solve. You have to give an instance of the example of that particular data set, and then the model is supposed to predict the output. Is this conceptually clear? Any questions here? All right. So I don't know if this is the right thing to do, but let me just scroll. Or should I go back to board? See, doing things by hand actually, they help us absorb them better. So, okay, let us do that. Okay, so this is the original text, and we are going to prepare the input in the following manner. Yes. So coming back to this, your original text is, thank you for inviting me to your party last week. Okay. Now input that you are going to give is thank you, and then instead of for inviting, use some some placeholder. Me for your party, so instead of last you put some placeholder week, and your model is supposed to predict, so it is supposed to predict x, and x should be replaced with for inviting, then y should be replaced with last, and then finally something to say I have nothing to do now. So this is just to say that I am done. You can think of it as end of sentence, something like that. Target, this is what you want to output. क्या चीज? राइट. हाँ हाँ See this, so this is the pre-training task T5 is trained on, and this looks closer to what? BERT. In BERT you had masked language modeling, here this is very close to masked language modeling. Okay. This doesn't have to be, just two continuous things, this could have been any continuous chunk. And so this is what it is, but which architecture is going to do this job for you? Encoder-decoder. So in BERT you had just the decoder. Okay. Now in this case you have encoder-decoder. Okay. So the architectures, so now I am going to, in fact this paper has so many figures that let me just go back there. So this makes sense? We are just seeing what is the pre-training task. So what is the pre-training task? This is something you are going to give input to whom? So basically these are nothing but masked tokens. Okay. You are going to give this input to encoder, and who is going to generate outputs for you? Decoder. So let me explicitly write this here. This is encoder and this is what the decoder does for you. So they talk about a lot of downstream tasks. So can you just look at these figures and figure out something that we have seen before? What is this guy? Decoder only, right? Because see what this is saying is this is your input and you are allowed to look at. So in self attention, if you are taking self attention in decoder, what will happen? Every token is allowed to attend to every other token. What about this guy? If you talk about masked multi-head attention, so masked attention, what is it allowed? So your first token is not allowed to look at second onwards, but your second token is allowed to look at first and second. Third token is allowed to look at first, second, third, but not at fourth and fifth, and so on. So you get this kind of thing. Okay. Remember that we had seen this masked matrix where there were minus infinities. Okay. What about this guy? So until some prefix, right, you are allowed to look at something, but later you are supposed to generate without looking at. So when you are generating, you are not supposed to look at everything, but before that you are allowed to look at everything that is there for you. Okay. What is this? How does this fit in what we are doing right now? See, this is encoder only, this is decoder only. I am trying to help this one. These two were easy. We have seen them many times before. What is this? So what about this part? You are always allowed to look at from x1 to x3. It does not matter whether you are at x1, you are allowed to look at x2 and x3. So there is some prefix length you are allowed to look at, so you are allowed to look at the whole input together, right? But when you start generating, right, when you start generating, you are not allowed to look at from there on. Okay. So let me see if, yes. So now I think the main takeaway of this is over, but let me just show you a couple of their results, right. Can you again help me figure out what is this? And see, they are drawing all so many things because they are comparing between encoder only, decoder only, encoder decoder for various architectures, for various data sets, for various batch size that you take. What else can you vary? For different objective functions and so on. If you see here, this is language model, and this guy is not allowed to attend to any of just drawings of what we have seen before, right. If you see here, x1 is allowed to attend to x2, x3, x4, x2 is allowed to attend to x1, x2, x3, x4. So this is a n square kind of thing, n cross n. This is not n cross n directly, I mean there are minus infinities sitting here, that is why you do not have these guys out there. So this guy can only attend to x1 and not x2, x3, y1, y2 and so on, okay. So now let me talk about a couple of results which actually don't, look at this one. This is important from future perspective what we have seen before. So they compare architecture, right. Right now objectives are, so everything else is same, but let us say architectures are different. So encoder decoder where model weights are shared, encoder decoder 6 layers instead of 12, language model, prefix, LM. You see here they say encoder decoder, which is T5, works the best. This is all bold. Then they say encoder decoder where parameters are shared, right. So your number of parameters become from 2p to roughly p, just half, not exactly half, there are details, but just half, okay. Cost remains m because you are still going to train them on this whole big network. If you see here, sharing parameters that does not hurt your performance, you go from 83.28 to 83.81, a slight minute difference. And if you see the first row and the second row, they are comparable. Similarly, again they say instead of 12 layers encoder decoder, you go to 6 layers in encoder, 6 layers in decoder. So you basically half the weight, and parameters are also half. It takes half, I mean the cost is half to train the half big transformer, and you see again that it does not hurt that much. From 83 you have gone to 80, that, so these are different scores. This is something that we should mark. They say language model, parameters are p, cost is m, and it becomes like 10 points lesser. So 74, 17, 61, the performance hurts much more here, S glue and so on. These are benchmarks, various data sets and their, so basically their matrices. So if you get this score on this, it is good. If you get lower score on this, this is bad and so on. हाँ. See, denoising is their objective, where you give this input, thanks, what was that sentence? Thank you for inviting me to your party last night. So denoising means I have given you a noised sentence that has these masks and you denoise that to give me the original sentence. So this is denoising objective. Okay. So objective remains the same, only architectures are changing, and they say keeping this language model actually does very worse. You know, rest everything is more than 80 on this, more than 18 on this, more than 77 on this. So they are all not very much off to the best scores. But C language model, right, this is very much far off from all of these guys. We are doing denoising. Denoising, language modeling is just what is the next token, and you are not allowed to look at what comes next. That is what language modeling is. Denoising is this example that we had talked about. Thank you for inviting me to your party last night. I am going to mask some things, and denoise means I am going to denoise those sentences. So those sentences, they had some noise like X and Y, and my model is supposed to reconstruct the original thing. So it is going to denoise the input. So what is the takeaway from these 5 lines? The decoder only model, the language model, right, it doesn't perform well and is probably not the right thing to do. And if you go and have a look at the presentation of this paper, they will clearly state, authors, see, it looks like either this or just the encoder is the right way to go. If you look at the papers, Google has, you know, focused a lot on things like Bert, Robert, I don't know. So there are so many names of Bert, Robert, Roberta, Albert, and I don't know which one comes from which one. So there are variants coming from Meta and all these things too. But T5 is from Google and so on. But from what I know, there was only ExcelNet that belonged to, you know, decoder only part. Primarily because the researchers there were thinking, in fact rightly so according to this data, that language model is not the right way to go. OpenAI on the other hand has stuck to just one thing, which is language modeling. Okay. So why I am spending so much time here? By 2020, people agree that there has to be a unified task. T5 gives you that. So what is the biggest takeaway of T5? You can ignore this whole paper if you want to, right? Not the right thing to do, but people have different priorities, so you can ignore this paper except for one thing. What is it? It unifies all the language modeling, all the language tasks, right? It converts every task as language input to language output. So you give the prefix of the job that you want to do, you give me the example of what you want me to do, I am going to understand what is this task and I am going to change this particular input according to that task, right. So if you see, this is what we wanted to achieve, and T5 has given us way to achieve this. This is the, so if you didn't understand anything today, it's okay. What you should still understand is T5 helps us to reach from here to here, because in the input itself you are giving me task and then input. So see, how does this might be working? Okay, I should stop. How does this might be working? See, beforehand you are telling me summarize, right? So I have a big model. So somehow you have told the model that summarize. So maybe some part of the networks will get, you know, activated to do summarization. When you tell me question answering, some another part of the network will get activated to do question answering, and so on, right? These are intuitions. You can't prove or disprove them mathematically. So I think that is it for today. That is it for T5. We'll go back to GPT-3. They do a lot of comparisons in this paper, and at least scroll through it. No, you need only encoder, decoder, that's it. Okay, sorry. Right, thank you. So, are you doing binary classifications here? Sorry, and thank you so much for this question. Right. So, what are the things on the right hand side? What do you mean by text to text? So, you are generating this. I mean, you are not having two classes here, acceptable and not acceptable. Your model is actually generating text saying not acceptable. So, it is not same as having two classes. You are still doing a softmax on all the possible tokens that you have. So, you are not taking, so output here is not two classes. You are going to generate not acceptable or acceptable. You are going to generate that text. So, it is not that in the end you are going to do binary classification, no. You are going to generate this text, and again if you listen to the presentation of this paper, they will tell you it did not happen even once that the model generated anything other than acceptable or not acceptable. So, this is not binary classification. You are taking text as input, you are giving me text as output. So, there are details to this, but this is able to generate numbers too, because numbers are in your vocabulary. So, what is generated here is 3.8, not a class. These are not classes, you are generating these tokens here like a language model will do. Thank you for this question. Anything else? In fact, we are done. More questions? Chalo.